Okay. So, let us get started. So, we are looking at Gale-Shapley algorithm and we are studying various properties of it. An important property is the main proposing version of Gale-Shapley algorithm is strategy proof for men. That means, any one man cannot get better partner by misreporting his preference, unlike women, right, we have seen. So, we want to prove this. So, it is again a proof by contradiction. So, we will assume that there exists an instance of stable matching where there exists a man who can get better partner by misreporting her preference. So, I think you have seen this notation. This means that just a tuple, just I am focusing on M. This and yeah. So, where this man M gets better partner by misreporting his ranking to be this. The output of Gale-Shapley on this actual input B m, and this is the input where this mth guy, mth man misreports, the output B m prime, and this guy M prefers his partner under M prime more than his partner under M. So, these are the assumptions, right, part of it. We want to find a contradiction. So, we have assumed that there exists a input where there exists a man who by misreporting can get better partner. I will find a contradiction. Everyone with me? Okay. So, let us draw something here. Here is A. So, let us use some color code. So, okay. So, let us look at this guy M. This guy has two different partners in two different matchings. So, this is his partner under M and this is his partner under M prime. Let us give some name, say W1, W2. W2 also has two partners, one is yellow partner, another is orange partner. Yellow partner is M, orange partner, can it be M? Can the orange partner of W2 be M? No, because M had different partner, different orange partner. So, the orange partner of W2 should be someone different. M prefers orange over yellow, right, that is by your assumption. M prefers orange over yellow. How about W2? Between orange and yellow, which one she prefer? Yeah.
M prefers W2 instead of W1.
Yellow.
Yeah.
Yes, correct. Thank you. Thank you. Yeah. M prefers yellow over orange. Yeah. Thank you. M prime. M prime prefers more. Yeah. Thank you. M prefers yellow over orange. So, how about W2 between yellow and orange? Whom she prefer? Between yellow and orange, answer is two options, orange or yellow. Orange. Why?
Because that is the actual mistake, right? So
Preferred M, they would have matched.
Sorry?
Is already taken. They had preferred
Yeah, priority to those guys who have not talked. Yes.
If so, it has preferred M1.
If I preferred M1,
If they have preferred M,
M,
like it won't be a stable match.
very good. So, you see this M prefers yellow, but W2 must prefer orange, because if W2 also prefer yellow, M prefers yellow, W2 prefers yellow, then M comma W2 is a blocking pair for orange matching. Look at orange matching, they are not matched with each other, but they prefer each other over their partners under orange matching. So, W2 must prefer orange matching over yellow. Okay, nice. Continue. Is M1 has also two partners, yellow and orange. This M1, which one does it prefer between yellow and orange? Yellow. Same reason, because if M1 would prefer, if M1 prefers orange over yellow, then because W2 already prefers orange over yellow, then M1 comma W2 will be a blocking pair for this yellow matching, right. These things continue. How long it can go on? I can ask these things. How long it can go on? Of course, everything is finite. So, either it will exhaust all men and women, or is there any other way to not exhaust and stop this process? This process cannot go on.
Until there is a yellow line towards W1.
Exactly. So, there is another way it can stop, is that you ask, you find who is the yellow partner, and the yellow partner turns out to be this. This way, these are the two ways how this can be stopped, this process can terminate. Okay. So, all these guys on the left, you see, they prefer yellow and their partners prefer orange. This is the root cause of all family jhamela. Okay. So, that is how we define two sets. A1 is the set of men. So, let us call it M1 in A, such that they prefer yellow. M prime of M1 is preferred by M1 over M of M1. I know this set is non-empty because by assumption M belongs to this set. And by picture it should be clear that if I look at these guys, this set who prefers yellow matching, their partners must prefer orange matching, and in particular B 1, if it is the set of partners of A 1 under M, this is also same as M prime of A 1. Pictorially, if you see for this men, if you look at the set of orange partners, these 3 women, the set of yellow partners, these 3 women. Okay. You can try to prove this formally, but I think this is pretty clear that their set of partners are same under both the matchings. All men in A 1 prefer yellow over orange, all women in B 1 prefer orange over yellow. Now, I am looking for contradiction. Now, run GS on this original input. To get M. So, you see the execution of Gale-Shapley algorithm on this input, how I am getting M. Now, here is a modified picture, here is A, here is B, here is A 1 and their partners are B 1. Okay. Let T be the last iteration when any man in A 1 proposes. So, Gale-Shapley runs for some number of iterations, and in every iteration one man proposes. You ask what is the last iteration where any man from A 1 proposes. So, let T be the last iteration where any man from A 1 proposes any woman. In that last iteration, suppose this is the man, let us call it M prime, who makes the proposal, that means in the Tth iteration. It makes a proposal to which woman? Can this woman be outside B 1? In the last iteration, the first question is, in the last iteration, which is the Tth iteration, where any man from A 1 proposes, let that man be M prime. Let us ask where does the possible woman lie whom M prime proposes? Can it lie outside B 1? No. Why?
Because it is the last person and is unmatched.
Correct.
Within A1, so it must get matched with someone in B1 according to our assumption.
Exactly. Right? Because it is the last time, M prime will get accepted. Now, if it gets accepted, its partners are in B 1. So, this belongs to B 1. And it accepts, let us call it say W prime.
This is due to assumption that M A1 is equal to M dash A1.
This is because of our assumption that T is the last iteration when any man in A 1 proposes.
This point where B1 is equal to M A1, this
This is not an assumption.
like, why is this true?
This I said from pictorial it is true, you can try to prove it formally, but it is almost clear from the process how I am defining this set A 1, and this I argued that whenever a man prefers yellow over orange, the woman will prefer orange over yellow, and from that argument it follows. Now, coming back, so M prime proposes to W prime, and that is fixed, because after that all the men never proposes, all the men in A 1 never proposes. So, this W prime is the final partner of M prime question. Okay, so W prime is the final partner of M prime. Can you tell me W prime is yellow partner or orange partner? Orange partner, because I am running this to get M. Orange partner, so let us draw it with orange color. This is the orange partner. Good. Next question. At the beginning of tth iteration, beginning means while loop just shuru hua, M prime when proposed to W prime was W prime engaged or free? Question. Yeah. Free? Why?
If it is not free, then that won't be last iteration. Right? If she is already paired with someone,
She
then
must be
this
paired
guy.
with someone in A1.
What if she is paired with someone outside here?
There will be another iteration to find a partner for that one.
But that is outside A1, that is fine, no? T is only for A1, this is important. T is not the number of iterations of Gale-Shapley algorithm. Not clear whether she will be free or not. Okay, let me tell you the answer, you tell me the reason. She is not free. Can you tell me why she is not free?
Because she would have gotten the yellow proposal.
Very good. You see, we are computing this orange matching. Now, in orange matching, every man in A1 prefers yellow partner, but they are getting orange partner. And this is the last iteration when M prime gets matched, that means all other men are already matched with orange partners. That means all men have already proposed their yellow partners. Let me repeat. I am seeing the run of this Gale-Shapley algorithm to get the orange matching. At the after tth iteration, or after tth iteration, all the men in A1 are matched with their orange partners, but all of them like their yellow partners than orange partners. That means all of the men must have proposed their yellow partners and got rejected within first t iterations. That means every woman in this set received at least one proposal. Make sense? Now tell me, where can, at the beginning of tth iteration, where can the partner of W prime lie? Can it lie in A1 or outside A1? Outside A1. It cannot lie in A1. Why?
If it lies in A1, then that person
Correct,
got
becomes
rejected.
free. Then T is how come T is the last iteration? So at the beginning of tth iteration, the partner of W prime must be some guy outside. And then she received an offer from M prime in tth iteration, rejected M double prime and get matched with M prime. That is the only possible way.
She was first in B.
No, everyone is in B. Sorry, please come again.
You wanted to see B minus B1.
No. So these are defined with respect to this yellow and matchings. It's not that they are moving. This yellow matching and orange matching are fixed. With respect to them, these sets are defined. It is not that at some iteration some main was in this part and then moved, it is not like that.
We are talking about the first iteration.
No, first I defined A1 and B1, these two sets with respect to these two matchings. Now I am seeing or focusing on the execution of Gale-Shapley algorithm on the original actual true input whose output I know is M. That execution I am focusing on and arguing about various aspects. And so, what we have seen is that in the beginning of Tth iteration, W prime must be matched with M double prime.
So that means she would be at in the B.
Everyone is in B, no? All women are in B.
After the first iteration, that W becomes W1 when she matched with M1.
W becomes W1.
W prime and M prime.
Yeah.
Maybe I am not getting something. Yeah.
Suppose that M prime,
M prime, correct.
no, M double prime.
M double prime.
M double prime was matched with W prime.
W prime, correct. At some
So
point.
she must be at A and she must be in B.
B1.
Outside B1.
Outside B1.
No, she is
Sorry.
always in B1. This A1, B1 are defined not in terms of iteration. They are defined in terms of these two matchings. How they are defined? I first define A1 who are the set of men who prefer their yellow partner over orange partner. And what is B1? B1 are their partners under any matching, they are same. That is how A1 and B1 are defined. It is not that in first iteration that someone is in outside B1, then it becomes inside B1, do not think like that, then you will get confused. So, these are sets, these are defined without this algorithm also. For these two matchings I have defined these sets A1 and B1, right, and now I am seeing the execution of Gale-Shapley algorithm on this input whose output I know is M, the orange matching, and then I am analyzing. Okay, now I have got many things actually. So, I know many things. For example, I know that W prime prefer M prime over M double prime, right, because she has rejected M double prime and accepted M prime. So, W prime prefers M prime over M double prime. There is some other yellow partner also. Okay, good. Can you find a blocking pair? It's not so much visible actually if I show then, but still I mean everything is there, we are just one step away from finding a blocking pair. Can you find a, okay, let me tell you something, can you find me a blocking pair for M prime? Blocking pair for M prime. Yeah, close. So, we will show that M double prime and W prime is a blocking pair for M prime, right here. For this what I need to show? I need to show that two things, W prime, M double prime W prime prefers M double prime over M prime W prime. This is what I need to show. Another is M double prime prefers W prime over M prime M double prime. These are the by definition. These are the two things I need to show. So let us try to show.
And it won't.
Sorry.
M double. So you are saying W prime prefer M double prime over M prime, right?
So you are saying that I have no hope to showing it.
No, what?
This is what I need to show, but you are saying it is not possible to show. But do you everyone agree that these are the two things I need to show? Okay. So let's try. Let's see. So first thing I need to show is that this guy is the yellow partner M prime W prime. M W prime prefers M prime this yellow partner this guy over sorry W prime prefers M double prime over this yellow guy. Is it not obvious?
Yellow guy got rejected.
So okay, you stop. Is it obvious to anyone? Yes, yours is correct. I need to show this. What does the first thing says? That W prime prefers M double prime over that yellow partner. Right? Now you see it is obvious because in the beginning of Tth iteration W prime was matched with M double prime, and I know that this yellow partner already proposed to W prime in the first T minus 1th iteration. That means W prime must have rejected, and so this is done. Now what I need to show is M double prime prefers W prime over his yellow partner. Is it obvious to anyone?
Yellow partner would be W hypothetic.
W? Somebody, I have not given her name also.
This is also true.
Yeah, he was saying something, yes,
This is also
sorry.
true because outside V1 and A1, all the matches are same in M and M prime. So that means
No, not like that. It's not that outside then they are same.
there should be no difference.
No, in A1, men in A1 prefer yellow over orange. So outside they can be either same or they prefer orange over yellow. A1 is the set of men who prefer yellow over orange. So outside A1 means their partner are either same yellow and orange partner, or they prefer opposite orange over yellow. That is what right. Sorry, you were saying something.
I was saying that it kind of comes from the fact that before the iteration M double prime was matched with W prime.
Correct.
So M double prime had proposed to W prime before this yellow matching.
That is not clear because I am running the simulation to get the orange matching. Yellow matching is not the output of this run of the Gale-Shapley algorithm. The output will be orange matching.
But he is going in his preference order.
Mm-hmm.
So he has proposed to W prime before the one who was not named right now.
Very
that
good.
means that W is
Yeah, you are very close. So let me connect the pieces. So you see this, because I am the output will be M, the orange matching. So eventually this M double prime will get matched with this guy. These two guys may be same also, I do not care. But what I know is that this M double prime prefers this guy over this yellow guy, or if they are same, right, because otherwise it should be in A1. either these two are same or this orange guy M double prime prefers over yellow guy, and how about between these two things, W prime and orange partner, whom M double prime prefer more? W prime, because W prime gets rejected and then you will propose somebody and then eventually this is the partner. So, from M double prime's perspective, W prime is preferred over M of M double prime, right. If M of M of M double prime is same as M prime of M double prime, if these two guys are same, then what I need, I have proved, I need to prove this. If this yellow and orange guy are actually same guy, then this proves this. On the other hand, if they are different guy, then between orange and yellow, whom it prefers? Orange, because it is outside A1. This case also gives us the result that we need to show. Yeah.
So I still didn't understand why outside A1 and B1 both would not be same, because we have seen
Sorry,
that
outside
outside
A1,
yeah, and outside B1
B1.
all the matches in M and M dash should be same, because if
Oh, let me yeah, say, please continue. Sorry.
because M is you are saying that orange one is more preferred than yellow one, and because it makes a cycle outside, because we are removing the same set of things, then there is no reason for yellow there is no reason for there to be any yellow matches, because all the oranges are more preferred than yellow.
No, I often get this sort of questions in my class, and the standard answer is this. Generally, I have, suppose I prove x greater than equal to y, and this solves my thing. Then it is like you are saying y greater than equal to, maybe greater, strictly greater than. So, without that assumption, even if without proving your thing may be correct, I am able to get what my result. So, so that is why means so whether that thing is correct or not may be correct, but that is not needed here for proving this. Do you get this sort of thing? Okay. But yeah, means I do not know, from a priori it makes sense, no, they can have different partner and this guy prefers orange, maybe, I do not know, yeah. Okay, but as I said, that thing is not needed to prove this. Question before I erase this entire board. Okay, so for any one man, it is not possible to get better partner by misreporting his preference in main optimal stable matching, in main proposing Gale-Shapley algorithm. Good. Okay. Now, let us come to his part that can we formalize this fair matching, why all either main optimal or woman optimal, can I get something in between, and for that let me introduce a structure, but before that we need this thing. here again another very surprising result, that let us have a stable matching instance. For any stable matching instance, take two stable matchings. As I said, there could be exponentially many stable matchings. Take two stable matchings M1 and M2 and assign each man to the, so this man M has two possible different partners M1M and M2M. Assign him to the best woman, whoever between M1M and M2M, whoever is preferred more by M, assign M to that woman. First of all, it is not clear whether it is a matching, right. Doing this, why every man is assigned to exactly one woman, it is not apparently clear to me. And second, why it is stable matching. Okay, so let us prove these two things one by one, but is the statement clear? Okay. So, yeah,
There are two men preferring the same woman.
exactly.
How would it be a matching?
Exactly. So, that is what I said, that it is not clear what I am defining, is it at all a matching, that is not clear. So, two things I need to show, that this definition makes sense, that you are actually defining a matching, that is not clear, that needs a proof. And once I do that, then next thing is stability, right. So, again these colors are nice. So, as you said, can I, is it possible that two men are matched with same woman? So, suppose it is possible. So, then let us suppose this M1 and this is M2, and both by following this definition got matched with this one woman W, and hence what you are defining is not matching at all, forget stability. Okay. So, let us analyze how, if this happens, then what other things break. So, again let us use two colors, M1 this orange, M2 yellow. So, suppose this is the orange partner and this is the yellow partner, somebody else, and okay, first let us kick out the easy cases first. So, first easy case is that this yellow partner is also this, can happen, no, a man gets same partner in both the matchings. So, if this man, if both orange and yellow partner is W, then can you give me a contradiction, assuming the fact that in this resulting matching that we are trying to define, there both M1 and M2 are getting matched with W. Not possible, but why?
It is the same woman, right? No one, it is not matching to other man for him to compare.
Correct, exactly, you are right. Others?
We are seeing here from M1's perspective only, no? Like it will choose better of M1 or M2 matching.
Correct, but
both
so
are giving the same.
then M1 is W and M2 is matched also with W. Why then M2 cannot be? Where is the contradiction if M2 is also matched with W?
M2 is matched to W. Like.
So, it is a proof by contradiction. So, first we prove two proof valid matching. Okay, that means this definition outputs a matching, that is what I am proving first, then stability. So, this part, So these are proof by contradiction. That means what? Suppose it is not a valid matching. Not valid matching. Not valid matching means what? It means that there are two men or two women, symmetric, doesn't matter. Two men who are matched with same woman. That's only, it may not be a valid matching. So let's assume that and find a contradiction. So first case is easy case, that suppose M1 and M2 both are matched with W, and W is both orange and yellow partner of M1. Then where is the contradiction? Sorry?
M2 can't be matched with W in either.
Exactly, correct. So then M2, can the red partner of M2 be W? No, because red is a matching. Can yellow partner of M2 come W? No, yellow is also matching. So then M2 cannot be matched with W. Easy. So now let's assume that M1, M2, their orange partner and yellow partner are different, right? Because if any one of M1's orange partner and yellow partner are same, then we have seen that it cannot lead to an invalid matching. So suppose this is a orange partner, and so if W is the orange partner of M1, W can only be a orange partner of M2, right? It cannot be a yellow partner of M2. It cannot be orange partner. I don't care. This could be somebody else or same also, doesn't matter. Okay. Now can you give me a contradiction?
So in our scenarios, which is better one?
Sorry?
Always orange is better. Yellow is
Both
better.
of them are matched with W. Both of them are matched with, they are better. That means for man M1, orange is better, and for man M2, yellow is better. That is how it is defined. No, I am matching every man with the better, and I am assumed that both of them get matched with W. So basically both of them like W.
So the final M that will be formed, that is when M1 and M2 are connected to W.
W, correct, exactly. And which we want to show cannot happen. So now can you give me a contradiction? Yeah.
Because the W will have a preference over M1 or M2.
Very good.
And it cannot happen that it will choose the
There is no point.
lower
No.
one when the
No. So get rid of Gale Shapley. In this here, there is no Gale Shapley. So M1 and M2 may not be output of Gale Shapley. So it's not that choosing, someone proposing, that business is not there.
But it is just not possible that M2 and W matches when M1 is her preference and M1 is still matched with somebody who is on a lower preference than W.
Very good,
It
but
will be
why?
an orange case.
Why?
Because
Yeah, someone had said blocking pair. Yeah, give me a blocking pair.
WM1 will be a blocking pair at W prefers M2.
Exactly. So you ask W between M1 M2 whom you like. So let's assume W likes M1. Doesn't matter if it likes M2. Same argument. Then see, there is a blocking pair. Where is my blocking pair? Then M1W. M1W blocks M1W blocks what? Yellow. Blocks M2. M1W blocks this yellow matching, because look at W. W prefers M1 than over yellow partner, right? W prefers M1 over her yellow partner. M1 prefers W over her yellow partner. So this is a blocking. This blocks M2. The other case you do, if it prefers M2, I think that may block the orange one. So this defines a matching. It cannot happen that two men are matched with one woman. got it. Although we are proving, but this looks like magic, means difficult to believe, lots of structure. Okay, so it define it so valid matching. So M is a valid matching. Now let us prove stability. So now let us clean up this. So to prove stability. So again prove by contradiction. So contradiction, assume M comma W is a so assume that it is not stable, and not stable means there is a blocking pair. Assume this is a blocking pair. Suppose here is M and this is W. Blocking pairs are not matched with each other. Right. Now, can you give me a contradiction?
So M is
Yeah,
M, the matching M is the result of M1 and M2.
correct.
So if there is a blocking pair M comma W, which means M is a better match than both M1 and M2, which can't be true.
Exactly. Unless they are unstable. Yeah, anyone else was saying something? Yes, so that is the crux of the argument. In this M, all the men are getting better, but your argument breaks from women's perspective. But the idea is sort of same, that if this is a blocking pair, I want to show that this is a blocking pair for one of these M1 and M2 also. So let us see. So suppose this is the orange guy, and so suppose the best for M is orange matching, then let us see what I have is W prefers, sorry, M prefers W over M1 of M, and let me write this way, and W M prefers M2 of M. And from W I know W prefers M1 over, sorry, M over one of them, M1 of W or M2 of W. I do not know which one, but one of them, right, because the partner of W is either her partner in M1 or M2. Now, if this part is true, then this is a blocking pair, using this is a blocking pair for M1. If this holds with M2, then use this, get a blocking pair for M2. Okay, good. Is this fine now? Similarly, you can prove that given two matchings M1 and M2, match every man to the worst of two partners. That is also a valid stable matching. Take again as a homework. Okay, not replace better by worse of two partners. That is also a stable matching, and these allows us to define the structure. Oh, it's fine. So, let this whatever fancy M be the set of stable matchings okay, this fancy M be the set of all stable matchings, and I am defining a relation on it, not relation, partial order. So, M1 M2 in M define M1 and M2 if every man is matched with better or same partner in M1 than M2. So, look at two stable matchings M1 M2. If it happens that everyone is, so every man is better off or same in M1 than M2, then we say M1 dominates M2. This notation is counterintuitive because we use the other notation for women. So, that is why this less than equal to, but M1 dominates M2. So, read it as M1 dominates M2. So, this is a partial order, this M and this is a partial order not only that, it has a lattice structure. So, let me recall the definition of lattice. Yeah. Sorry.
So, we proved that suppose there are two stable matchings M1 and M2, and if you take the best for men, it gives a stable matching. We also assume that if you take the worst, it gives a stable matching.
Correct, yeah, that homework.
So now if you take the worst for women among the two, that also gives a stable matching because men and women are symmetric.
Yeah.
But we haven't proved that the worst for women matching and the best for men matching, they are the same yet.
That I gave as a homework again.
Okay.
In the, I think in the first class something like that. That the output of men proposing Gale-Shapley algorithm is omen pessimal. In particular, what it means is that every omen is matched with a man who is worst among all possible stable partners.
This is something even stronger that I am asking.
Sorry.
M1, M2, take the best for men. So let's call that matching M prime.
Correct.
Now take M1, M2 again,
Okay,
will we get M prime?
I think so. Yeah, and this follows that argument. You know, yeah, I'm tempted to give it as a homework, but okay, let's see. Basically, what I have proved is that whenever you take two matchings and look at any man, suppose this guy, it has two partners. Now, if this guy prefer yellow, then the yellow partner must prefer orange. So, use that to prove that. So, what he is saying is also very important. What he says is that, okay, how do I define M for every man, assigning it to the best partner? Let us do the other way, for every woman, assign that woman to the worst partner, and these two are same matching. You can prove this using this sort of argument we did some time ago, that basically every man who preferred yellow over orange, that yellow partner must prefer orange over yellow. And so, it is like if I pick yellow, then these are not only good for men, they are simultaneously bad for women, because all yellow partners of those men who prefer yellow, those partners prefer orange. So, for every man choosing yellow, yeah, correct. So, for those set of men, so you can divide into three things, three parts. Here, yellow and orange are same, doesn't matter, nothing to choose. In this region, men prefer yellow over orange. So, basically what you are saying is that for this men prefer yellow partner, which is same as saying for their partners prefer orange, because these sets are same. For a set, these we proved in that strategy proofness, I think, that if I look at the set of men who prefer yellow over orange, their yellow partners and orange partners, they are same set of women. And here also, here will be things so it opposite. In this set, every man prefer orange over yellow, but if you are picking for every man the better woman, then here you are picking orange matching, which is same as saying for this woman you pick the orange matching, something like that. But yeah, you can take it as a homework also, not difficult. All the ingredients are there. Let us come back to lattice. So, distributive lattice is a partial order say S and something such that, so it is a partial order with some more property. First is for every pair of elements x y in S, there exists a least greatest common upper bound. What is this terms? Least upper bound. Yes, LUB, least upper bound. I think denoted by X, this thing. Yes, I got very confused, and this is called meet or join. Meet, okay, thank you. This is called meet, right? Meet or join.
These terminology just enter meet join. That's easy.
Join.
This is join, okay. and the second one is greatest lower bound for every greatest lower bound. Is called meet. Okay, so just a one liner. So this is basically among all upper bounds the least one. So it in a arbitrary partial order there is no reason why such a least upper bound can exist, because we are in a partial order case, there are elements who are incomparable. So I can have two upper bounds which are not comparable, but among all upper bounds there must exist at least one which must be comparable with everyone, and not only that, that should be least. So it is an extra property. So least upper bound, similarly greatest lower bound, and the third is these two operations distribute over one another. So for all x, y, z, yes, x this and okay. So these are the properties, and now let us come back here. So I have just defined partial order. Now I need to define how do I define least meet and join, least upper bound and greatest lower bound, and this is basically this theorem I just erased. So let me define. So M1, M2, two stable matchings. So define, not define, into prove that M1 join least upper bound. So this definition makes sense if you have two stable matchings, assign every man between two possible partners the worst of them, worst woman, that we have shown that that defines a stable matching. So this belongs to M, and from the definition this, let us call this matching M. So what is clear is both M1 dominates M and M2 also dominates M, but that is not enough to prove that this is a join of M1 and M2. What you need to also show that among all such matchings which is dominated by both M1 and M2, that dominate M also, that they is least upper bound, oh sorry, I think this is greatest lower bound. Yeah. So M1 dominates M because every man in M is getting the worst of M1 and M2. So M1 dominates M, M2 dominates M. To show that this is a greatest upper bound, you need to show that any other matching which is dominated by M1 and M2, M dominates it. So this is clear. Show what if M1 dominates M star and M2 dominate M star, implies M star dominates M. It should be opposite. Yeah, M dominates M star, correct. So, this I have not proved, again let me give it as a homework, easy, few lines. Okay, this is for this operation. For the same other operation also you do the other way, that you define M1, this we have defined meet, then I define join. Okay, this is for all M star in M. For all stable matchings only you have to define. This is matching, calling it M prime, every man with better of M1 and M2. So, what is clear is M prime dominates M1 and M prime dominates M2, and again you need to show this sort of thing. What you need to show? Show that if M star dominates M1 and M star dominates M2, then M star dominates M prime for all M star in M, and then these two properties that distributive law holds. So, using this what you get a lattice structure, and once you have a lattice structure you can, what you take, you can define a concept called longest chain in a lattice. In a finite lattice you have a longest chain, and once you have a chain, in a chain the concept of median makes sense. So, for this lattices you can draw Hesse diagram and this sort of thing, it is lot of structure. So, there is a longest chain, the long chain is what? So, chain is a sequence of elements, consecutive elements dominate, and in that longest chain compute the median. So, that in some sense fair, because the highest one at the top which dominates everyone is the main optimal stable matching. And this is omen optimal in the longest chain. So, from fairness perspective it makes sense to find a stable matching which is median in this chain. So, people have studied this problem and it is quite extensively, it has been studied how you can compute this. Gale-Shapley outputs either this or this depending on who is proposing. So, this is what I meant by formalizing the stable matching which is in between or equidistance from main optimal and omen optimal.
What is the purpose of taking the longest chain?
Because in the longest chain you get at one end main optimal, other end omen optimal. So, it is in some sense if you look at the median that is equidistant from this main optimal stable matching and from this omen optimal stable matching. Yeah.
Distributive lattice of current all chains of same length, like from when to unit.
Yes, I think so. No. So, chain you can, for example, you can take this, any sub chain. You can say you want to maximal chain.
When optimal women optimal stable matching appear in every chain?
Maybe maximum.
Maximal chains. Because you can, any singleton set is also a chain, singleton thing. Any two thing is also a chain. They are comparable. Maximal chain, yeah.
How will you interpret the median? What will you say it will be optimal for some men or some women?
No, so this is the formal definition of median. Median of a chain makes sense. It's a finite set, finite chain. And the median is a chain is a order. In the order, the middle point is the median.
So
if it is even, take anyone,
like
even
you
or
are saying the top one is optimal for men and the bottom one is optimal for women.
correct.
So the median, what would you interpret the result of a median?
It is, I don't know, it is somewhere in between men optimal and women optimal. That's all. That, yeah, that's
Because more you move towards the man optimal, you are getting more and more fair, like
correct.
more biased towards the
Men,
men.
correct.
And if you move, so it's like a toggle switch. Say somewhere stay in the middle.
Like some men will get
Or men are
best
keep
partner
getting better partners.
and the woman will also
so
get
like
some best partner.
some women will get best partner or like everyone will get maybe their second best
No,
choice. Or
so as you move along the chain, for example, so here compared to this, here every woman, so this outcome is Pareto better than this outcome.
no one will get their best
Worse.
choice.
No one will get worse. Some guy keeps improving.
So everyone will get maybe the middle of their order or something like
That's difficult to say, not middle of the order, but we have to say clearly.
that. Like can some, there would not be any guy who will get the best possible.
That those are difficult to say.
Yes, because some man may have the exact same partner in all
Exactly.
the relationships.
Exactly.
So do we have deterministic algorithms to reflect the median or somewhere around?
This again not top of my head. That do you recall?
Median?
Yeah.
Median is hard to find.
Hard to find.
So you
NP
can't
complete.
generally.
Yeah. NP complete. If you try to be fair to people, this is what happens. Yeah. But this is a good news for we are in IMSC. Once you have NP complete, then you have lot of things you can do. We researchers, then you have lot of research scope. Then many things open up. You can do approximation, parameterization, and various other things. And this is just a tip of iceberg, not even tip of iceberg. Many things. Actually, Pallavi will explain many more things. Some more computational tasks and those. Many medians. Give me any. Correct. So typically, if you draw, it basically looks like this. There are various chains. So give me any.
So there might be exponential number of
Medians also. Correct.
That is unlikely, right? Because chains and anti-chains have a relationship.
Yeah.
And so just take the set of medians, they lie on an anti-chain.
Correct.
Actually, the first one, second one, they are comparable, right? So it will be like top one and the next one, it will be like
Yeah, comparable. Yeah.
so every man will get a better.
Better or same.
But
Yeah.
similarly,
Correct. Exactly. So this age means whenever I have an age, for example, from even here to here, that means every man here is as good as, and at least one is better, because there are two different matchings. So there are some men, at least one man, who are getting different partner. So that for that man, the partner should improve because it's a strict ranking.
how do you get them different changes?
How do you get so these are defined with respect to these operations, and so it can happen that this matching and this matching is incomparable. So that's where you get the different chains. The entire thing is not a chain. Yeah.
Sir, so I'm assuming the length of the maximal change is also exponential, right?
That can be more L.
Yeah, that is not. That cannot be, because if this is the best for men and this is the worst for men.
Only N possibilities.
If it's polynomial, then can I not just solve
What is polynomial?
the length of the maximal chain?
It is at max N. But there are many chains.
There are many chains. The whole lattice is exponential size, right?
Yeah, no, I'm asking ki the length of.
How do you know the length of the chain is order n?
I'm asking like is it
I don't
exponential
know.
or polynomial?
I don't know.
You see,
Right?
let me see. I think
You can't bound the size of chain, right?
no. So you see, whenever let's start from top. I'm just thinking loud. Let's start from top. Whenever you go down one step, you are moving, you are improving at least one man once. For every man, you have n improvements. So total improvements you have is n square. So you have n square budget. So this length can be at most n square.
Okay, correct. Because anyway, rotation, you have to have at least one rotation per. Okay, yes, that's true. Length is n order n square, correct. That holds from.
So you can ignore that rotation business, but the basic thing is that for the nice people like me, whenever you go one step down, at least one man will get what's now कितना नीचे नाम कितना नीचे गिरेगा at most n.
But what's the rotation thing? Sorry, I didn't.
You don't have to. We'll see in the next class.
But is it not simpler? I don't know. People don't like simplicity.
No, I was just.
No, I don't think it's simpler than rotation.
No, I was just asking like.
We'll hear in the next.
Yes,
It's a
yes, yes.
teaser, let's say.
Yeah.
So even if it is n square, to find even one chain, we don't know how to do.
Yes, think of longest path.
No, we can. Okay, so we can just keep on. I don't know how to. We can find a chain by just doing rotation.
No, I can find a chain.
But there are a lot of chains, right?
Yeah.
Again, the rotation is exposed, then negative. As long as you can go, then there are no rotations to expose. You have reached one rotation.
Correct, but why it is the longest? Is it a longest chain? If it is the longest chain, then
Not necessarily.
correct. That's the problem. There should be some part hard. But I think we can stop here and then we can keep discussing on.
Yes,
Yeah.
yes, we can stop here, right.
Okay.
So I think the next class.
But yeah, these are good questions. So it seems this chain you can find, but that need not be longest chain.